For any chemical equation, we model it using a chemical reaction. We know that the term reactants refers to the materials that we're starting with, what we call the chemical species. And then those things produce the stuff on the right side of the chemical equation called the products. When you're reading this sentence out, we use the word yield or yields to refer to the arrow in the center. In writing the chemical equations, there's a number of different special symbols that we use to represent what are the conditions of the reaction, what things have to be present, or what state of matter do the different reactants have to be in, or the products form in. So for example, here we see some different symbols on the left and what they mean on the right. Some really common ones that we're going to come across are the triangle over the arrow. That indicates that heat needs to be applied to initiate the reaction. Usually this is used to overcome activation energy or those sorts of things. Other common ones that we're going to see are the examples down here, where we have a little tag next to the element symbol. Those tags are used to indicate the phases because a lot of time reactions happen only in certain phases. So for example, only if they're aqueous or solid. Also knowing what phases they produce helps you indicate or know if a reaction is happening or figure out what different things your products might be. For example, what is the gas or what is the solid forming at the bottom? So let's take a look at some example chemical equations. For the example one, we have liquid isopropyl alcohol is reacting exothermically with oxygen in the presence of heat to form carbon dioxide gas and water. So if I take that sentence, I can write what's called a word equation by just pulling out the different words to represent what are the chemical species that are being reacted, what is being produced, and what are the reaction conditions. So here I see first that isopropyl is reacting exothermically with oxygen. So I have isopropyl and oxygen as my two reactants. Exothermic means that energy is going to be produced in the reaction. This reaction only occurs in the presence of heat, which gives me my special symbol over the arrow here. And then this reaction produces carbon dioxide gas and water. So looking at our product, carbon dioxide goes here with the G to indicate it's a gas, and water vapor, we have water here, and this is indicating that it's a vapor as well, right? Because we know vapor is the gaseous state of matter. So this word equation is good for reading it off, but a lot of times when it comes to doing the calculations, balancing, which we'll talk about later and such, we need to have chemical formulas. We can't just rely on the chemical names because we need to know how many atoms of each are present and I'll be able to work with them in that way. So what we usually do is after getting a word equation like this, we just write all of the chemical equations or chemical formulas for each of those things just directly down from where they went. We decided in the special symbols that energy is usually just represented by E. Water we know is H2O. Carbon dioxide, now that we're all confident in our covalent compound nomenclature, is CO2. We also just know covalent nomenclature. Now the formula for oxygen is going to be a tricky one because it is not just O. It's O2. Because oxygen is one of the 7 diatomic elements. And these are the ones that we just need to know. We did make a note of them on our periodic tables back when we were first labeling and coloring our periodic tables. At this point, you just need to have them either memorized or referenced somewhere. If we were in the building, these would be used so often that it's just going to be drilled into our heads. But anytime you see the elements hydrogen, oxygen, nitrogen, or any of the halogens, chlorine, fluorine, bromine, or iodine, those 7 elements are so reactive that they'll bond with themselves in the absence of anything else. So they're always going to exist in pairs. So oxygen isn't just going to be O, it's always going to be O2. And then isopropyl alcohol is named isopropyl using organic chemistry nomenclature, which is something you'll deal with in college when you take that, or perhaps in bio if you're an AP. But that formula is just given to us, C3H8O, to get our chemical equation there. Our next example is going to be iron wool reacting with oxygen gas to produce iron 3 oxide when initiated by an electrical current. So when initiated by an electrical current tells me about my reaction condition, which is represented by the little electrical symbol over the arrow here. What else do we have? It's iron metal reacting with oxygen gas, so iron as a solid, oxygen as a gas, and it's producing iron 3 oxide. Iron 3 oxide is an ionic compound. Ionic compounds have extremely high melting and boiling points, which means they're almost always going to be solid unless it's dissolved in water, but there is no water present in this reaction. Turning this into a chemical equation, symbol for energy is E. Oxygen again is O2. Iron metal is just Fe. And then iron 3 oxide, we need to bring back our ionic compound nomenclature. So for this, we know that iron 3 refers to the iron with a 3 plus cation. Oxide is O2 minus. So to make those charges balance, I would need 2 irons and 3 oxygens, Fe2O3. Let's take a look at those two reactions really quick. So from those reactions, we can see that as the iron metal is burning, the mass is actually increasing. And as the isopropyl alcohol is burning, the mass is going down. So same reaction, but two apparently different results. And the reason we have to keep this, what we have to keep in mind is when the isopropyl alcohol is burning, it's producing two gaseous products, meaning that as they're produced, they're going to be going up into the air, up into the atmosphere. However, when the iron metal is burning, it's producing a solid, which means that it's going to be present still on the weighing dish there. Now, it makes sense that this first one's going to be measuring at a lighter mass as it burns because it's starting to lose material. It's not going to be present in that dish anymore. It's not present in the liquid as it turns up into a gas. However, for the second reaction with the iron, we're starting with a solid, and we still have a solid at the end, except now the solid at the end has a bunch of extra stuff in it. It has all of these oxygen ions that were originally dissolved up in originally present in the gaseous form up in the atmosphere that are now being solidified in this ionic compound, which is why the mass of the iron metal is going to be increasing over the course of the reaction. So this idea brings us into another important law. It's very related to what we talked about earlier in the year with the law of conservation of energy, but we have the law of conservation of mass. And that's the idea that during any chemical reaction or physical change for that matter, the total mass of the reactants is equal always to the total mass of the products. We talked about in nuclear chemistry how this wasn't necessarily the case. This was the whole idea behind mass defect. But the reason there was a mass defect in nuclear reactions was because the forces were so much stronger that it accounted for an actual significant change in the mass. By comparison, what we found the mass defect for a chemical reaction, it is a fraction of the mass of an electron. It's so tiny that it's essentially insignificant to anything we're going to ever do in chemical reactions. Now, the problem with our chemical equations right now is that they don't agree with the law of conservation of mass. Because when we wrote our chemical equation for iron burning with oxygen, we came up with this equation here at the bottom. But if we look at that, there's only one iron atom on the left, but there are two in the products. We had 2 oxygen atoms on the left, and we have 3 in the products. Right now, we have more products than we do reactants, which is not possible. We cannot create stuff over the course of the reaction. So in order for this reaction to occur, it needs to be balanced. We need to have the same number of atoms on the reactant side and the product side. And by balancing it will help us figure out what are the ratios that these reactants must combine together to get the products. And that's going to be the topic of our next video.